Kia ora. My name is Zachary and I will be presenting about how we revisit the foundations of supernova 1A cosmology using Pantheon plus data. As a general note throughout, whenever I'm referring to type 1A supernova, or supernova in general, I'm always referring to type 1A supernova within this presentation, just for ease. So first, just a little bit about our how to find our research and the team. So I myself am a first-year PhD astrophysics student at the University of Canterbury, studying supernova cosmology and other transient discovery/analysis. Please keep me in mind when I apply for postdoc positions in a few years, or if you're really nice, please talk to me so we can set something up. Antonia Seifer is just about to start a PhD in Canada after finishing her Masters. At this conference, she will be presenting her Masters work on general relativity in galaxies, and I do recommend looking at that. We also have Ryan Ridden Harper, who's a postdoc at the University of Canterbury studying supernova and other transient phenomena, alongside David Wiltshire, a professor at the University of Canterbury in gravitation and cosmology, who is also giving a talk on our group's work and a general overview of all of it. Finally, we have Marco Galoppo, who is a part of the letter that that is upcoming and the extra work we are doing. He is doing his PhD in mathematical physics on general relativistic models on galactic scales. He is also giving a talk, and I would highly recommend going to see that. Now, what is our motivation? Why are we doing what we're doing? What is the need for cosmologically independent analysis? With the recent DES photometric supernova 1A results casting some doubt on the standard model of cosmology, there's now more need to perform cosmologically independent analysis. With this in mind, our analysis of the Pantheon plus supernova 1A data is cosmologically independent, even from the FLRW metric. Now, that does mean, unfortunately, we do not contain peculiar velocity corrections, as there's no way we can do that in a model-independent method. However, we are in the talks with the team at the University of Queensland to see how we can start to implement some of these features. We also compare the standard model with the timescape cosmology. For those who aren't familiar, it is an inhomogeneous non-FLRW cosmology. It is classified by the parameter the void fraction and has the same number of free parameters as a spatially flat ΛCDM model. It has passed every single observational test that has been thrown its way. So now let's talk about type 1A supernova and standardization. So, the equation on the left is the trip equation. It is the equation that is generally used to fit supernova curves to bolometrically correct the magnitudes that we observe. This is done with the spectral adaptive light curve template, or SALT, and is now the standard used for supernova standardization. Pantheon Plus uses a modified SALT-2 algorithm, while the new recent DES survey uses SALT-3. So I'm now going to break down what each of these mean so that we can all understand what's going on. So, what we have here are the SALT-2 fit variables. This is what the light curve template is actually fitting for. So we have the apparent magnitude and the B filter. We have the X1, which is the stretch. You can think of it as like a time delay or a time squashing or stretching of the photometric light curve. And we have the C, which is the color, which is usually typically related to the offset and prominence of the measured measured magnitude in that band. We also have the cosmology fit constants, alpha and beta. These are fit alongside the cosmology as free parameters. They are determined to be constant for all redshifts. However, beta has been observed to not actually be a constant across all redshifts. However, it is constant within the region that the universe is statistically homogeneous, and we will discuss statistical homogeneity soon. And then finally we have the absolute magnitude and the B filter. By definition, this is a constant as it is defined to have no stretch and no color. Alright, Pantheon Plus. So Pantheon Plus, we consider a total of 1690 spectroscopically confirmed Type 1a supernova, which is the largest spectroscopically confirmed collation of Type 1a supernova. They exist in the redshift range of near 0 to 2.26 redshift, with 31% of the data being below 0.033 heliocentric redshift. Now that works out quite well for us because the large number of low redshift data is good for this type of analysis and testing statistical homogeneity. Now, using the provided data, we have made a covariance matrix which is independent of cosmology, including independent from the FLRW metric, which is commonly assumed. So now let's discuss spatial homogeneity. The main question to ask is, at what scales can we consider the universe to be homogeneous? In the standard model of cosmology, the lambda cold dark matter, it is assumed that the universe is isotropic and homogeneous. And this is true on large enough average slices. But what is the scale at when it is suddenly homogeneous? In the standard model, that is typically given between a redshift of 0.02 and 0.04. However, there are some questions to ask. How much does local structure, e.g. voids and filaments, affect observations from afar? How much does the motion of these structures relative to us account for systematics in observations? You'll notice I've plotted on the graph on the right the SHS of the 2-point galaxy correlation function, which is the typical metric that is used. So we have looked at this and we decided, can we find out when the universe is statistically homogeneous using light curve parameters only? To find the scale of statistical homogeneity, we look at empirical statistics based purely on the supernova light curve parameters and when they converge. So for this we use the alpha x1 degenerate product, and we see when that converges and stops shifting. Using this, we find a SHS of in the CMB frame of 0.075. We cannot use the beta C degenerate parameter, as Malmquist bias cannot be done in a model independent method. However, we are talking again with the team at the University of Queensland on if we can do this in a method for timescape which is fair for comparison. Further tests will be done with GR simulations. I would recommend listening to a talk from another person in our group, Michael Williams, about these GR simulations and their exciting discoveries, who's also speaking at this conference. These GR simulations, they have the same initial conditions coming from the CMB power spectrum, and their initial preliminary results return a comparable redshift value for the statistical scale of homogeneity as what we get. So now let's look back at our SHS and overlay the value we found. As you can see, our SHS alpha is twice as large. This doesn't necessarily mean that the lambda cold dark matter model is wrong. However, it does mean that we have to pay more careful attention as a community to the regime for which we apply corrections for different levels of our cosmic distance ladder. For if our most local stuff is incorrect, that could propagate further to create further tensions at higher redshifts. So now we're going to go to the crux of our analysis, Bayesian analysis. So I know not everyone is familiar, so I'm going to give a quick overview of the graphs and how to interpret them. So along the y-axis we have the log of the Bayes factor, where 1 or -1 represents positive evidence, and 3 represents strong evidence, and 5 represents very strong evidence. If the line is in the blue, that means it prefers timescape, and if the line is in the red, it will always prefer spatially flat lambda cold dark matter. Along the x-axis, we cut data below certain redshifts in the CMB frame, and we do the same analysis with different sets of data to see how the universe evolves. We did also compare, which is the top graph, compare to other subsamples and how the redshift distribution affects the statistical evidence. So throughout you will be able to see, I guess, a subset of the data that was in previous analysis for JLA. Now, let's start breaking this down in different regions so we can help break down and understand what's going on to make it more palatable. So the first thing to consider is the full sample contains a greater density of low redshift data. The full sample shows near strong evidence in favor of timescape, which is expected. Spatially flat lambda cold dark matter doesn't work that well within this regime, as it's not designed to, as the universe is not considered homogeneous. Timescape, however, accounts for quasi-local effects, so it can work at much closer scales to us in the late universe. Now let's discuss what I call the calibration regime. This is the regime for which the lambda cold dark matter model should be the most effective, as it is the region it is calibrated to based on the statistical homogeneity scale of the two-point galaxy correlation function. In this regime, we see the shift from no statistical preference to near strong evidence in favor of the spatially flat lambda cold dark matter model. This is not necessarily unexpected, as this is the regime for which the spatially flat lambda cold dark matter model works best. Now let's break into our last regime, the SHS alpha regime. In this case, the subsample yields no statistically conclusive answer, but possible positive preference in favor of timescape. However, the full sample shows no statistical preference between the two models in the SHS alpha regime. I will make a comment: it is never expected when the universe is homogeneous that there should be strong evidence for either side, because if there is, it shows that one of the models is not fitting to the observations quite that well, and both models are designed to match to observational data. So, now there's a question. Everything before that had the bias that we considered x1 and we modeled x1 and c as Gaussian distributions, which isn't quite true. But what happens if we model using only the SALT2 best fit x1 and c and we don't assume an underlying distribution? So that's what we get as the trip formulation. Now I will say a caveat of this method is the assumption that the SALT2 parameters represent the most probable values for x1 and c for this version of the SALT model, potentially overlooking astrophysical systematics inherent in the SALT2 values. Despite the distributional caveat, this method optimizes individually for each supernova rather than relying on a general distribution. With that in mind, we will look at the cosmological parameters. Particularly, we'll be looking at the void fraction, as less people are familiar with it. So, we have realistic parameters within 2 segment for independent GR simulations, which will be talked about by Michael Williams, and I do recommend seeing those results because they are very interesting. Furthermore, we are within 1 sigma of the predicted value from based on the CMB fit values done back in 2013. We are also within 2 sigma of independent lensing catalogue fit values found by Chris Harvey-Hawes, and I would recommend seeing his talk about the details of that. Now, let's analyze the evidence. Once again, let's break this into the different redshift regimes. In the low redshift regime, we can see that there is both strong and very strong evidence for timescape over spatially flat lambda CDM. Now this is not a surprise, as timescape is designed to work once again at closer redshifts than what's the average slicing of spatially fat ΛCDM it will. Now let's look at the calibration regime. Here we see positive evidence for timescape, leading into no statistical preference in the calibration regime. Now, if I was to squash the previous results over these, you'll notice that the features are all the same. However, they've been shifted up in favor of timescape, where before we had near strong evidence for ΛCDM, now having no statistical preference. And finally, in our SHS alpha regime, we have positive evidence for timescape. And again, strong evidence is not expected observationally, as you're considered to be within the Hubble flow. Alright, what if we now assume that there is a multivariate asymmetric Gaussian distribution for x1 and c? Well, that's going to be further work. In Seifert et al. In prep, our letter, we will test multivariate skewed distribution statistics modeling for x1 and c. We also have more work on investigating the SHS alpha and its implications, some of which I have discussed, and I also want to perform similar improved analysis with the new DES supernova data when that is made publicly available. I've talked to the team that have done it, and they've done some great work with it. We also have some more fun surprises currently in the process of being run. In summary, empirical supernova parameter statistics find a scale of statistical homogeneity twice as large as what is currently used for calibration, with a redshift in the CMB frame of 0.075. In the late universe, we get very strong evidence for timescape over the standard model of cosmology in the trip distribution formulation, and near strong evidence in the Gaussian formulation. In the scale of statistical homogeneity regime, timescape is positive evidence over the standard model in the trip distribution formulation, and no statistical preference in the Gaussian formulation. And because of the recent DES and DESI results, we need to test other models, as these can teach us important astrophysical and cosmological concepts. So just quickly to wrap up, please feel free to join our question session if you happen to have any questions. Otherwise, we are open to further discussion about what we did, our data set, and feel free to contact us. Also, remember to please consider me or headhunt me in a few years when I am looking for postdoc positions. Thank you very much.